Okay, ready?
Yeah, so.
Okay, so remember what we're trying to do? Anybody remember what we're trying to do?
It's been a while.
It's been a while, sorry. Remember the last, any memories of, yes, Hadamard?
Hadamard Factorization theorem.
Right, the factorization theorem. So we just did the Weierstrass Factorization, and now we're going to go after the factorization of Hadamard for entire functions that have a finite growth, finite order of growth. Right, so it's like a special case. Right? Weierstrass is for the general entire function, and then this is for entire functions of finite growth. Okay. So, and it turns out to be a lot more complicated. You can get a stronger result, but it's the proof is pretty intense. So I'm not even sure if we're going to finish it today. It may take 2 classes to finish it. So here's the statement of Hadamard's theorem. It says that if you have an entire function and it has an order of growth rho, and you let k be the largest integer smaller than or equal to rho. I think this is called the floor of rho, if you know that term. Then if we let the a sub n be the non-zero roots of f, and in that case, f can be written as e to the p of z times z to the m times e sub k z over a sub n goes from 1 to infinity. Okay, where p is a polynomial of degree less than or equal to k, and m is the degree of 0 as a root of f. Okay, so this was the statement of Hadamard's theorem. And remember what's different about it between this and Weierstrass's theorem is that you can have that p is going to be a polynomial and that the k is constant, right? That the k, remember for the Weierstrass theorem, we had n, e sub n, and as n goes from 1 to infinity, right? So the degree of the canonical, I'm sorry, not the canonical, the elementary factor changed with the root. And here we're saying that we can take just one fixed number there for k. Okay, so I'm going to sort of remind us of how we proved. So let's recall how we proved Weierstrass factorization. So if you look at the proof, you'll see that we actually proved a result. We actually used the following result. So I'm going to sort of codify what we did in the proof of Weierstrass. Okay. So if you have a domain, and you have a bunch of holomorphic functions on that domain. If for every compact set K in your domain, there exists an m sub n that can be dependent on the set such that one, it controls the size of that of the holomorphic function for all points in the compact set, and for n equals for all n, and the sum of the m sub n's was finite. Then the function that is the infinite product of 1 plus the phis converges uniformly. So that infinite product converges uniformly to a holomorphic function. Okay. When we proved Weierstrass, right? So uniformly on K and to a holomorphic function on omega. Okay. So I don't know if you remember the proof of Weierstrass's factorization theorem, but the way we did it was we proved it on disks. We proved it on an arbitrary disk, and then we said, since we proved it on the arbitrary disk, then we've got it on the whole plane, right? And so this is basically the same sort of thing. This is just taking the process of that proof and codifying it into a theorem. Okay. So like the proof of Weierstrass was in the proof of Weierstrass's theorem, we have a sub n goes to infinity, right? We have a bunch of roots, and we assume that the roots went to infinity, right? And our phi sub n were the difference between e sub n scaled so that it had a 0 at a sub n and 1, right? And then for any k compact in C, there existed some n such that for n greater than n, we had z over a sub n was smaller than half for all z in the compact set. Right, because the a sub n's, so I'm just running through the proof of Weierstrass again, okay, right? In the case of Weierstrass, we're looking at the product of things like the product of the elementary factors, right? If we look at the if we fix a compact set, well, since the a sub n go to infinity, well, at some point we're going to have it so that for any point in the compact set, z over a sub n is going to be smaller than half in size, right? Because the a sub n's go off to infinity, and compact means bounded, right? Closed and bounded, right? Okay, so since now remember we had this bound on e sub n, right? That the difference from 1 was controlled by some constant times z to the n plus 1, right? Remember this? This was our bound on the elementary factors, right? And so what does that give us? Sorry. That gave us that the phi sub n, which are exactly that difference, right? Sorry, let me stop trying to save space and go over here. Okay, the phi sub n are e sub n z over a sub n minus 1, right? So that's controlled by z, I'm sorry, by c z over a sub n to the n plus 1, right? Yeah, the n plus 1. Right? But that's smaller than c times 1/2 to the n plus 1, right? By our choice of n. Right? So for n bigger than that n, we have this bound. Yes? Right? And since of course this is finite, right? These things here are our m sub n's, right? Since the sum of those guys is finite, right? Since the sum of those guys is finite, then we get that, you know, the product of e sub n z over a sub n is a holomorphic function, is an entire function. Right? It's a holomorphic function on C. Yeah.
Is the constant C fixed or?
It was fixed, yeah.
Okay, but like for all?
For all n's.
Gotcha.
Yeah.
Okay, good.
Yeah. Okay. Okay, so this is how we got Weierstrass's Weierstrass factorization. Right. It may look a little different, but this is essentially the proof that we gave. Any questions? Anybody stuck on anything? So, right, we have this result. This result is basically like a kind of Weierstrass test for products. Weierstrass test for products, right? That if the difference from 1 is bounded and then the sum of those bounds is finite, then the product of the functions is holomorphic, right? Then the product converges uniformly to a holomorphic function. Okay, and we said, well, look, if you have any compact set, then you can get this thing smaller than a half, right? And then you just use the bound that we got on the distance of the factors from 1, and that just gives it to immediately. Okay, so that was Weierstrass. Okay, so now we're gonna go for Hadamard. Okay. So the first thing we're going to do is see that we can create the function. Okay. So is it okay if I erase this? People still copying? Okay, so step 1 is basically the first goal is to see that f. So realize f as e to the gz, z to the m, e sub k, z over a sub n. Okay, that. Okay, so the first goal is really to show that this thing actually converges. Okay, and that's not the hard part. The hard part is to show that this thing is actually this g is actually a polynomial. That's going to take forever. Okay, but anyway, we'll do it. Okay, so So let's recall some facts that we proved about functions of finite growth. So if f is an entire function of growth order rho. And we denote by a sub n the non-zero roots of f. We denote by n of r, again, the number of non-zero roots. It could be all the roots are non-zero. It won't make a difference. You can say, like, without loss of generality, it's the non-zero roots. Number of non-zero roots of f in the disk of radius r around 0. Okay, we showed two things. One, that the number of roots was controlled by the rate of exponential growth, right? And we also showed kind of a sparsity condition that if you take any s bigger than rho and looked at 1 over the absolute value of the root to the s power, then that actually turned out to be finite. Okay. So there were two things that we proved. One was this, like control on the number of roots, and the other was something about like how spread out the roots had to be. Okay. So okay. So again, we'll let. So notice that. Again, let's denote the floor of rho as k. Okay. So in particular, summation 1 over a sub n to the k plus 1 is finite, right? Because k plus 1 is bigger than rho. Okay, and so what we need to do is we need to show that what we're going to do is show that that this thing, the product of these guys, where k is fixed, actually converges uniformly. Okay. Once we show that, that will give us the form of Hadamard's of the function, the form of the factorization, right? Because then we'll know. Then z to the m times this thing will be an entire function with the appropriate roots, with identical roots to f, right? And then when you divide out, you know that f over this guy has to be of the form e to the g, right? Because it'll be an entire function without any zeros, and we've showed earlier that entire functions without any zeros can be expressed in this form. So that will give us, once we show this, that tells us what the function has to look like, right? And then all we have to do is show that g is a polynomial. Okay. So let me go over here. Yeah, space. Okay, so this actually turns out to be pretty straightforward. So for proof of the claim. Let K be compact. Sometimes people use this notation. I like using obscure notation. Let K be a compact subset of C. Whatever, compact subset of C. Okay. Do you guys know what this notation is?
It's proportional to, right?
Yeah, very good. It's proportional to. I think I first saw that. I had a class with Conway. Do you guys know this name? John Horton Conway. I had a class with Conway, and he had used that in one theorem. Let me see. I can tell you, if you don't mind, I'll tell you a funny story about Conway. Conway was kind of a big, he's like this big British guy with like a big beard and bobbed hair. Like his hair sort of went down to here like this, and he had a beard. Anyway, enough about his appearance. He was sort of like a very bombastic kind of guy. And one time, it was a course in representation theory, and David Grabner, who was the son of Sandy Grabner, who used to be a math professor at Pomona. He retired maybe like 5 or 6 years ago. But David Grabner was in the class, and Conway put up some result, and then Grabner like raises his hand and he says, "Professor Conway, what happened to Frame's theorem?" And Conway like turns around and looks at him. He goes, looks at the board. He goes, yes. What happened to Frame's theorem? Aren't you an annoying little man? Anyway, that's the end of the story. I've never used that phrase, but wouldn't that be kind of classy to say at some point? Like, aren't you an annoying little man? I'm not big enough to use it, I guess. Yeah. Okay. Yeah, what are we doing? Okay. Yeah. So let K be compact. Yeah. Okay. Let K be compact. Then consider. Right. So as before, we're going to let E sub n be E sub k. Sorry. No. Z over A sub n minus 1. And we want to show that thing has bounds on K, the right kind of bounds on K. So what's the point? That you say, well, look, this thing is just as before. This is just by definition, of course, but just as before, we get the bound that this is controlled by Z over A sub n quantity to the K plus 1. Right. Okay, but K is compact, right? So we know that this thing is controlled by the supremum of this CZ to the K plus 1 as Z ranges over K, everything over A sub n to the K plus 1. Right? This number is finite, right? Because Z is compact, right? And so we're going to call that our M sub n, right? And if you look at the sum of the M sub n's, well, that's just this constant on the top, which I'll call C sub capital K. That's going to be C sub capital K times summation 1 over A sub n to the K plus 1. But we just saw, we showed last time that that's finite, right? So that's finite, and that gives us that by the tool that we codified, this thing actually, oops, this thing actually is entire. Okay, so again, this is kind of a Weierstrass kind of result, Weierstrass M test kind of result, where we're using basically the Weierstrass M test. Any questions? This is actually more straightforward than what we had to do for the Weierstrass. I guess it's about the same. But. Okay. So, like I said, now all we have to do is show that that G is a polynomial of degree less than or equal to k. For that, I need a new notepad. I should say that this presentation is based on some notes that I found from my old a guy who was a TA at Princeton during my first, he was the TA for our classes during our first year at Princeton, named Jerry Sherman. He's now a professor at Reed, and I found his presentation. So he wrote up these notes to clarify this chapter, and I found his presentation a lot clearer than Stein's. Okay. Okay. So now we want to show that G is a, and I'll send you all his notes. Okay. We want to show that thing is a polynomial. And to do so, we're going to use the following theorem, or lemma. Okay, so here it is. Suppose that G is an entire function, and let U be the real part of G. If there exists an S greater than or equal to 0, such that U of Z is less than or equal to C times Z to the S, absolute value of Z to the S, for Z that equal Ri, I equals 1, 2, 3, blah, blah, blah. So maybe I should explain what the Ri are. So Ri, any sequence of positive numbers, positive radii, such that Ri go to infinity. Okay, so if there exists an S such that you have this sort of bound on circles whose radii increase to infinity, okay, and that C should not depend on the I, okay, then G is a polynomial of order less than or equal to S. Okay, so this is basically saying that if you have an entire function and its real part has this sort of bound like a polynomial, it has this kind of polynomial bound, but not necessarily on the whole plane, but just on radii that increase to infinity, then G must itself be a polynomial. G must be a polynomial. Okay. So that's what we're going to use in the end, but let's show this thing first. Okay, so here's the proof. G is entire, so let's expand G in its power series expansion. A sub n z G. Okay, so now recall that we had this connection between the Fourier series and the coefficients of the power series expansion. So we had this result that the Fourier coefficients of G in a circle of radius r equaled the power series coefficients times r to the n for n greater than or equal to 0, and were 0 for n less than 0. So this was this connection between power series coefficients and Fourier coefficients. Not exactly the same function, but anyway. Okay. Okay, so we're going to take that and then change it into a connection between the a sub n and the real part. Okay, and we'll get the real part by just taking the complex complex conjugate of this and then adding it together. So okay, so we have this relationship, right? And then you take the conjugates of both sides, right? You get G conjugate R d I theta. The conjugate of this is going to be E I n theta d theta, right? Equals a sub n r to the n a n conjugate r sub n for n greater than or equal to 0, and n for n less than 0. Right. So I just took conjugates of both sides. Right. But notice that I can rewrite the left side. I'm just gonna flip the n. Okay. So this is going to be r d I theta e to the negative I n theta d theta equals this for n less than or equal to 0 and 0 for n greater than 0. Yeah. No.
In step 2, when you took the conjugate,
Mhm.
why did the I in the re to the I theta not turn into a negative I?
That's argument. That's the argument of the function. So I'm just taking the conjugate.
I see.
Right. It's like I took f conjugate. You don't have to conjugate the z. Right.
Right. Okay.
Yeah. Yeah. So when I write this, I mean this.
Okay.
If that. Okay. Okay. Everyone all right? We just took the conjugate. Okay. And now we want to get some statement about the real part. So we're just going to add them together, right? So for n greater than 0, we're going to add these things together. We get twice this, right? G plus G conjugate is twice the real part. So we get twice the real part. Equals a sub n r to the n. Right? Because I took this guy, right, and then I added it to this guy. Right. and you end up with 1 over 2 pi times the integral of g plus g bar, which is 2u evaluated this. So you get the Fourier, Fourier coefficients of u. Well, twice them. Okay, so okay, so let me just write that as write that again as negative a sub n is 1 over pi r to the n integral of negative u r di theta e to the negative I n theta d theta. Okay, and now I'm going to slip in a cleverly disguised 0. Okay, so this is just a constant, right? This is a constant with respect to theta. So all I'm slipping in is this CRS times e to the negative I n theta, right? Wait, remember n is bigger than 0, right? And this is just 0, right? This is just 0 for n bigger than 0. Okay, so we slip in a 0. Okay. Right, now remember, we assumed that u of z was controlled by C epsilon value of z to C epsilon value of z to the s, right? That is that u re I theta is controlled by CRS, right? That's the CRS that I'm slipping in here. Okay, so now let's take the absolute value of both sides. We get that this thing is controlled by 1 over pi Rn times the absolute value of the inside. Right? So we're using the triangle inequality, right? This thing is positive by assumption, right? This thing is positive, so it just stays as is. Right? So this thing is positive. This thing has size 1, right? And so we get this. Okay, right? The CRS, of course, doesn't depend on theta, so we end up with CRS times 2 pi, right? Times 2 pi over pi Rn, right? We also end up with a 1 over Rn, 1 over pi integral from here to here, u r di theta d theta. Okay. If I put a 2 on the bottom and a 2 on the top over here, then you recognize this thing. This thing is actually if you do the similar thing, this thing is going to be the real part of the real part of the 0th coefficient, from the power series expansion. Okay, that's what this thing in the circles, in the parentheses is. Okay, so you end up, this equals that, right? So here you get this CRS minus N. Right. Right. So what does that tell you? Right. That tells you that whenever n is bigger than s, right, plus some constant. I'm sorry, plus 2 real parts of this thing over r to the n. Yeah, over r to the n, right? And so what does that tell you? That tells you that whenever n is bigger than s, then this is going to go to 0, right? We let remember our r's. This statement was true for r's that went up to infinity. So let the r's go to infinity, right? Let the r's go to infinity as long as n is bigger than s, we get 0, right? So that tells us that you know that this thing stops at degree k. Right. So degree of g must be less than or equal to k. Yeah.
When we take the absolute value of both sides with the an and the integral over there, like where does it, like, do we bring the absolute value inside the integral?
That's right. That's right. So that's why there's that less than or equal sign here, right? So we take, you know, absolute value of the left-hand side is controlled by the absolute value, the integral of the absolute value on the right-hand side, right? And this term is positive, so it stays as is. This term is size 1, so it just vanishes, right? And so we're just left with this. Okay. Okay, so you see where the maybe you see where the finite growth is gonna come in here. That's the S. Okay. So okay, so we're actually we're going to finish this time. Okay. So okay, so that's now we have this tool, right? We have this tool to show when g is a polynomial. Right. All we need to do is get some sort of control on the growth of the real part of g. Okay, so now goal still show g is a polynomial. Okay. Before we do that, we're going to reduce the problem using the lemma we just proved. Okay, so here's the claim that we can actually reduce this problem to yet another complicated bound. Okay, that I don't know if you'll like it or not. It's a pretty cool bound. Okay, so. Okay, so the claim is that will be done if we show that if we can get this kind of bound. Oops. E to the negative c s for z equal size r sub I for a sequence r sub I that goes up to infinity. Okay, so so choose what's S. Choose any S such that S is between rho and k plus 1. I think strictly greater than, yeah, strictly greater than rho. Okay. Suffices to show that we can get this sort of bound for a sequence of increasing radii. Okay, I'm going to say that that'll do it for us. That'll give us that G is a polynomial. Okay, so why is this enough? For then, if we multiply by z to the m, that thing is still going to be big, still going to be bounded below by our bound. Right? And thus, if we look at the absolute value of e to the gz, which is the same thing as e to the uz, u being the real part. That's going to be, right, so we have right, f is this thing, right? So f is we have that, right? So of course, this is equal to this over that. Right? But we know that f is of finite growth, right? So f is controlled by some a e to the a b z to the rho. Oops. Right? We know that f is of finite growth, and we know that this guy is bounded below by this, so its reciprocal is bounded above by e to the c czs. Right. So what does that tell us? Right. That tells us that this guy is bounded by the bounds of f and then times the bound for the reciprocal, right? Yeah.
Between the claim and the proof, why are we able to add a z to the m term inside the?
Because z is going off to infinity, so it's just going to get bigger.
I see. So okay, I understand.
Like we have this. And definitely we have this, because this is a number bigger than 1. Right. Right. Z is the size of z is r, and r is going to go off to infinity. So, zm times that guy is certainly bigger than that guy. Right. So. We can definitely throw in a z to the m. Is that okay? It's like
Yeah.
saying.
I
okay.
think I understand that. I maybe don't understand why we can discount the case where it's like I understand it goes to infinity in the limit, but okay, that's all right.
Are you worrying about? Okay, so maybe for a large enough I.
Okay, yeah, I see.
Yeah. Or we can just say such that all the Ri are bigger than 1.
Yeah.
It won't affect the proof at all. Yeah.
Okay.
Yeah. Okay. Everybody all right here? Right. So, right. We know that f looks like this. We can write e to the gz as this quotient, right? We have a upper bound for f. We have a lower bound for the denominator. So of course we have an upper bound for the reciprocal of the denominator, right? I mean, we have a reciprocal for the anyway. We have a bound for it. We have a bound for it, right? Right. And right. And s is bigger than rho, right? S is bigger than rho, and so we can write this as e to the some constant z to the s. Okay. Everything can be subsumed into that. All those other constants can be subsumed into that c. That's a different c from this c. It's pretty common practice to just use one simple, use one constant, and it changes every single time. Okay. Okay, but what does that tell you? Right? That tells you that u of z is controlled above by this thing. Right, and that's exactly what we showed. What we need to show that g is a polynomial of degree k, less than or equal to k. Okay. Okay. So now all we need to do is the last. Pretty awful technical lemma. So here we go. This morning I was thinking, maybe for the final exam, I'll just ask them to prove Hadamard's. You have 3 hours. Okay, so here's the technical lemma. I did have one final exam like that in graduate school. Like during the first year of University of Chicago, it's on a trimester system. You take 3 classes every trimester. So there's nine classes you take. And the way you get out of the master's program and into the PhD program is to at the end of the year, there's a master's exam where you take one exam on each of those portions, right? There's like a nine part exam on those classes. They changed that actually. They changed that right when I got there. So I didn't have to do it, and the class before us was the last class to do that. So they were very bitter. Anyway, one of the classes on group theory. The professor just asked us he just gave us a huge list of theorems, and he said, I'm going to ask you to prove, theorems from this list. And so we just had to memorize however many dozens of theorems there were. Yeah, which was not that hard. I mean, it was a pain, but not hard.
Classify all the finite simple groups.
Yeah. It's Conway who was really one of the masters of that. Right? He discovered, I think, the monster group and stuff like that. Yeah, he was involved in that. Okay. So the technical lemma, right? We need to show that for some sequence Ri, where the Ri go off into infinity, that we have this lower bound Okay, so first notice that for zeta less than or equal to half, negative log 1 minus zeta equals summation zeta to the j over j as j goes from 1 to infinity. Okay, so what's the point? E sub k of z is defined as 1 minus z times e to the z plus z squared over 2 plus z to the k over k, right? But we write this as, this is going to be, of course, e to the log 1 minus z times that. Right? And then you just cancel off, right? So you get that e sub k of z is e to the negative z to the j over j for j greater than k. Right? Because you lose the first k terms. Okay, so we're going to go for this bound, but we'll go for it in parts. Okay, so we'll split the roots into two groups. Okay, so first case, the first set of them is where the a sub n are such that z over a sub n is less than a half. Right? So for the large a sub n's. Okay. So then, well, we want to control this thing. E sub k is z over a sub n. Well, by definition, as we just said, well, that's going to be e to the summation, sorry, negative summation z over a sub n to the j over j as j goes from k plus 1 to infinity. Now that is greater than or equal to e to the minus that sum, the absolute value of that sum. And that's just because the absolute value of e to the w is greater than or equal to e to the minus absolute value of w. Okay. So then we say, well, now we're going to try to get a lower bound on this thing. So let's get an upper bound on this thing, right? And oops. Right. This thing, of course, is bounded above by, using the triangle inequality. It's going to be bounded above by this. Right. By triangle inequality. Right. And then we just factor out a z to the k plus 1. So we say, well, that is equal to z over a sub n to the k plus 1 times z over a sub n to the j minus quantity k plus 1 over j. I'm not doing anything, not doing anything fancy here, right? Now the z over a sub n is smaller than a half, right? So this is this is smaller than the sums of powers of a half, right? So this is smaller than 2. And each of these guys is smaller than 2 to the appropriate power, right? So it's smaller than the geometric series for a half, right? And so that gives us 2 times this thing. Okay. That's an upper bound. That's an upper bound, and so taking negative this gives us a lower bound. Okay. And so we get this is greater than or equal to e to the negative 2 z over a sub n to the k plus 1, which we'll rewrite as e to the negative 2 z over a plus n, k plus 1 minus s, and then z over a sub n to the s. Okay, k plus 1 is bigger than s, right? K plus 1 is bigger than s, so this is a positive value, right? And so we get that this is greater than or equal to e to the e to the negative. We use again the fact that z over a sub n is smaller than a half, and we get this, and we get z over a sub n to the s. Okay, so that's the bound for each of these guys for each of the roots. Now we're going to multiply them all together, right? We're trying to deal with, right? We're trying to get a lower bound for this thing, right? We need to control. We're going to control the product where all the roots are big, and we're going to control it when all the roots are small. Okay, so when the roots are big, we get this sort of bound. Okay, and now we say, well, let's see that we can control that product, right? So here's the bound we get, right? We get that this guy is controlled by this thing here, below, bounded below by that. So now we multiply all those guys together. So thus, if we take the product over all roots such that z over a sub n is smaller than a half, right? And look at the size of that. Well, that's going to be bounded below by the product of all these guys, right? But you see what happens, right? That is that's the same thing as e to the negative 1/2 k minus s, absolute value of z to the s, summation 1 over a sub n in absolute value to the s. Right? Just by, exponential, okay? By products of exponentiation, right? So, and we assume that this thing, when we multiply over all roots, is finite. So when we add over all roots, this is finite. So this is finite, right? And this is certainly finite, right? So we get e to the negative c, z to the s. so that allows us to control the product over the roots that are large. And it looks like next time we'll control the other part, the product over the roots where the roots are small. Okay, we'll get a similar bound. We're going to have to use that. That's where we're going to need the R. That we won't be able to. So this bound holds for all. But the next bound we're going to only be able to do it on certain radii, and that's so we'll need that condition to get the lower bound for those guys. Okay, that's it.
Do you have our exam?
I'm sorry, I don't. I'm trying.
No, that's okay.
Yeah, sorry. Okay, are you guys all right?
Yeah.
That's it's pretty heavy.
How did Hadamard come up with this?
Right. Isn't it so wonderful? Right, like, right, like, right, but you can sort of see the desires, right? Like,
Yeah.
you want to do this. Okay, you've got this result. Okay, we're gonna have to do something like this. You know, you can sort of see what he had to. He knew he had to do, and then he pulled it off somehow. Yeah, but no, it's just wonderful.
I like how we have to bound it away from 0, but these infinite products are funny.
Say it again?
I like how we have to bound it away from 0, like bound it from below, because infinite products are funny.
Yeah.
Like just like things that you don't have to do for an infinite sum, you now have to bound this away from 0 because we're dealing with an infinite product now.
Yeah.
Just
Yeah.
interesting.
Okay. See you guys next time.